Hey fellow nerds, today we'll solve all the gate problems on OpAmp circuits from 2015 to 2020. In part 1 of this video, we have already solved the problems from 2020 to 2024. Here is our first problem. The components in the circuit shown below are ideal. The OpAmp has positive feedback and the input voltage Vi is a sine wave of amplitude 1 volt. What we have to find out is if the output voltage is a non-inverted sine wave of 2 volt amplitude, or an inverted sine wave of 1 volt amplitude, or a square wave of 5 volt amplitude, or a constant of either 5 volt or minus 5 volt. Now, this is a pretty simple question once you recognize the circuit over here. You can see that the input is given to the positive terminal. The feedback is also positive. So the feedback will reinforce the input instead of opposing it. Which means what we have over here is a Schmitt trigger. And we know output of a Schmitt trigger is always saturated. So the output will be a constant of either 5 volt or minus 5 volt. Because we sat here are 5 volt and minus 5 volt. Option D is the correct answer. Let us see the next problem. We have a circuit given over here and the OpAmp is ideal. What we have to find out is the voltage in volts correct to 1 decimal place at node A, which is over here, connected to the negative input of the OpAmp. First thing you have to do is to identify the circuit. Here the input is given to the negative terminal and the feedback is negative. The feedback is negative because we are taking potential from the positive of the output and giving it back at the negative of the input. So this is an inverting amplifier. Then the output will be negative of R2 by R1 multiplied by the input. R2 is 31 kilo ohm, R1 is 1 kilo ohm, input is 1 volt. So V output ideally should be minus 31 volt, but there is a problem. Vsat is only plus or minus 15 volt. So the maximum negative value we can have at the output is only minus 15 volt. What we need is more than that. Minus 31 volt is less than minus 15 volt. So the output will be saturated and the output voltage is going to be minus 15 volt. Now in the figure we have a point over here that is called A. What we have to find out is actually the voltage at A. Usually we know that whatever is the potential we have at the positive terminal, that is exactly what we have at the negative terminal because of virtual ground. Then potential at A should be equal to 0, right? Wrong. Virtual ground does not apply here because the voltage output has already been saturated. Virtual ground is only applicable if the OpAmp is in linear region. Over here, we already saw that the output is much more than the maximum value we can have and the OpAmp is in saturation mode. So virtual ground does not apply. VA will not be equal to 0. So to find VA, let us apply Kirchhoff's current law at node A. If you take a look at this 1 kilo ohm, it has a potential VA on one side and it has a potential 1 volt on the other side. So if we take the direction of current through it this way, that means this current will be VA minus 1 divided by 1 kilo ohm. Now for the 31 kilo ohm, it has VO potential on this side, VA on this side. If we take the direction to be like this, then that current will be VA minus VO divided by 31 kilo ohm. According to Kirchhoff's current law, the sum of these two currents should be equal to 0. We already found that VO is minus 15. So all we have to do is substitute that over here and find the value of VA. We get VA is 16 by 32, which is equal to 0.5 volt. So the most important thing to keep in your mind while solving a problem like this is that do not assume there is virtual ground concept unless the OpAmp is in linear region. If the OpAmp is in the saturation region, virtual ground does not apply. Let us see the next problem. In the given circuit, the OpAmp is ideal and the zener voltage of the diode is 2.5 volts. At the input, unit step voltage is applied. That is, V in as a function of time is just U of t. Also, at t equal to 0, the voltage across each of the capacitors is 0. What we have to find out is the time t in milliseconds at which the output voltage V out crosses minus 10 volt. Let us figure this out. Let us see how the circuit can be modeled at t equal to 0 plus. At t equal to 0 plus, the input just switches from 0 volt to 1 volt. We know capacitors cannot charge instantly. So at t equal to 0 plus, when the input just goes from 0 volt to 1 volt, both capacitors can be modeled as short circuits. I'll call the first capacitor C1 and the second one C2. Now, since C2 is shorted, basically the zener diode is being shorted. So let us remove the zener diode from the circuit model because it won't do anything. Again, the input just went from 0 volt to 1 volt. So at the input terminal, all we have is a 1 volt. Let us show it like this using a cell. The positive terminal is grounded. According to virtual ground concept, here also we'll get 0 volt. Now, if you take a look at the 1 kilo ohm, it has 0 potential on one end and 1 volt on the other end. So it will have a current flowing in this direction, which is equal to 1 minus 0 divided by 1 kilo ohm. Let me call it I naught. Now, I naught cannot go into the OpAmp because the OpAmp is ideal. So I naught will flow through the 1 kilo ohm and then flow through C1 charging it. So we can say I naught is the initial current that flows through C1. The value of I naught is 1 minus 0 divided by 1 kilo ohm, which is equal to 1 milliampere. Now I naught will flow through C1 and eventually through C2. Both capacitors will start charging. As they get charged, the potential drop across them also increases. At some point, potential drop across C2 will become 2.5 volt. Remember, we have a zener diode over here, and the zener diode needs at least 2.5 volt across it so that it can switch on. So when the potential across C2 becomes 2.5 volt, the zener diode will switch on. When that happens, we can model the circuit like this. Capacitor C1 is over here. Capacitor C2 is also over here. Since the potential across C2 became greater than 2.5 volt, the diode switched on, and because of that I modeled it as a cell whose potential is 2.5 volt. As the capacitors charge, obviously the current will decrease. So I am calling the current I. I naught was the initial value of I. Again, at this point we have 0 volt. Current flowed in this direction so that C2 could be charged. That means C2 has positive potential here and negative potential here. Again, since C2 is shorted by 2.5 volt, potential across C2 will be 2.5 volt. For C1 also, since current flowed in this direction, it will have positive potential here and negative here. Now, according to the question, we have to find the time t at which the output voltage becomes minus 10 volt. That is, over here we should get minus 10 volt. Let us now apply Kirchhoff's voltage law in this loop. At this point we have 0 potential, so we can assume this to be the ground. As I go on, I have the capacitor C1 across which there is a potential from positive to negative. Further, as I go on, I have C2 who also has a potential across it positive to negative. We also know the value, it is 2.5 volt. Further, we have V out from positive to negative, and we go back to the ground. So I can write VC1 plus VC2 plus VO is equal to 0. We already have the value of VC2, it is 2.5 volt. VO, according to the question, is supposed to be minus 10 volt. So by substituting these two values, we can find the required value for VC1. VC1 will be negative of VC2 plus VO. VC2 is 2.5, VO is minus 10. So we get VC1 should be 7.5 volt. At time t, potential across C1 should be 7.5 volt. We already know the initial value of current through C1, it is I naught. So the potential drop across the capacitor C1 at a time t is given by the expression 1 by C1 integral from 0 to t I naught dt. We have to find the value of t at which this becomes equal to 7.5 volt. We know C1, it is given in the question, it is 1 microfarad. We know I naught, we just found it, it is 1 milliampere. Let us substitute the values. 10 to the power minus 3 divided by 10 to the power minus 6 is 10 to the power 3. Integral from 0 to t dt is t giving the limits from 0 to t. That gives us t is 7.5 millisecond. The output voltage will become minus 10 volt at t equals 7.5 millisecond. Option C is the correct answer. Let us see the next problem. In the voltage reference circuit given in the figure, the OpAmp is ideal and the transistors Q1, Q2 up to Q32 are identical in all respects and they have infinitely large values of common emitter current gain. The collector current IC is Is e to the power VBE by VT, where Is is the saturation current. Assume that the voltage Vp shown in the figure is 0.7. Vp is shown over here. The thermal voltage is 26 millivolt. All we have to find out is the output voltage in volts. Let us figure this out. The first thing I want to do is to simplify the circuit. I'll take the OpAmp. Negative terminal is over here. Positive terminal is over here. Now, in the original figure, from the negative terminal, we have a 20 kilo ohm that goes back to the output. Let us show it over here. We also have a 5 kilo ohm at the negative input that goes to Vp. Let us also show that. Now, the positive terminal goes to Vx. From Vx, we have a 20 kilo ohm that goes to the output. Now at X, we have a transistor connected. So its collector current will be flowing in this direction. Let us show it over here. Since it is the collector current of the transistor Q1, I'll call it I1. How about at P? We saw that all the transistors are identical. So all these transistors will have the same collector current. At P, we have 31 transistors. So 31 times the collector current of one of these will be flowing in this direction over here. Let us show it at this point like this. 31 I. I being the collector current of one of these transistors. So this is the final circuit model we are going to use to solve this problem. Let us start by calling this point A and applying Kirchhoff's current law there. For the 20 kilo ohm, it has V out on one end and VA on the other end. So if we take the direction of current to be like this, then the current will be V out minus VA divided by 20 kilo ohm. For the 5 kilo ohm, it has VA over here and VP over here. So the current in this direction will be VA minus VP divided by 5 kilo ohm. According to Kirchhoff's current law, these two currents will be equal. Now, using the virtual ground concept, VA will be equal to Vx. So we can write the same equation this way. V out minus Vx divided by 20 is equal to Vx minus 0.7 by 5. Why is Vp 0.7? Because it is given in the question that Vp is 0.7. Now, the current flowing through the 5 kilo ohm resistor is actually 31 times the collector current I. What is I? I is the collector current of one of these transistors. We can write it as Is e to the power VBE by VT. Now, Vp is the potential these transistors get at the base. At the emitter, they have 0. So the potential difference between the base and emitter is Vp minus 0, which is Vp. So we can say this is equal to 31I, where I is actually Is e to the power Vp by Vt. Also, this equation can be simplified and written like this. It gives us a relation between Vout and Vx. We get Vout is 5Vx minus 2.8. Let it be there. Let's take a look at the 20 kilo ohm over here. It has a potential V out on one end and Vx on the other end. So the current flowing through it in this direction will be V out minus Vx divided by 20 kilo ohm. But this is the same current as I1. So we can write I1 is Vout minus Vx divided by 20 kilo ohm. But I1 can also be written as Is e raised to Vx by Vt. Vx because for the transistor number 1, potential at base is Vx. Potential at emitter is 0. So VBE, potential difference between the base and emitter, will be Vx. Now see this. Here we saw 31 Is e raised to Vp by Vt is equal to Vout minus Vx by 20. Here we see Is e raised to Vx by Vt is also equal to Vout minus Vx by 20. So we can say I1 is equal to 31I. That means Is e to the power Vx by Vt is equal to 31 Is e to the power Vp by Vt. Is and Is can be cancelled. Let's take log on both sides. If you take log of e to the power Vx by Vt, you will simply get Vx by Vt. How about if you take log of 31 times e to the power Vp by Vt? See, log of x multiplied by y is log of x plus log of y. So log of 31 multiplied by e raised to Vp by Vt is log of 31 plus log of e to the power Vp by Vt. And log of e to the power Vp by Vt is simply Vp by Vt. So we get Vx by Vt, which is the log of this one, is equal to log of 31 plus log of e to the power Vp by Vt, which is Vp by Vt. We can simplify this and write as Vx minus Vp is Vt log 31. Vt is 26 millivolt. Vp is 0.7. So we can easily find the value of Vx. It is 0.789 volt. Now here we have the equation Vout is 5Vx minus 2.8. We found the value of Vx. So we get Vout is 1.145 volt. The output voltage in volts is 1.145. Let us see the next problem. The amplifier given in the figure is implemented using a compensated operational amplifier. It has an open loop voltage gain 10 to the power 5. Its open loop cutoff frequency is 8 Hz. What we have to find out is the voltage gain of the amplifier at 15 kHz frequency. First of all, we have been given the open loop voltage gain. We need the closed loop gain because we have a feedback over here. For that, let us first find the feedback factor. Feedback factor beta will be R1 divided by R1 plus R2. Here R1 is 1 kilo ohm, R2 is 79 kilo ohm. So we get beta is 1 by 80. Using beta, we can find the closed loop gain. Closed loop gain is open loop gain divided by 1 plus open loop gain multiplied by beta. Open loop gain is 10 to the power 5. Beta is 1 by 80. Giving the values, this is what we get. Let us divide the numerator and the denominator with 10 to the power 5. Then we get 1 divided by 10 to the power minus 5 plus 1 by 80. In the denominator, we have 10 to the power minus 5 plus 1 by 80. This is a very small number, so we can say this is approximately equal to just 1 by 80. That makes this 1 by 80 or 80. Again, from the question we can see that when voltage gain is 10 to the power 5, cutoff frequency is 8 Hz. We have to find the cutoff frequency when the gain is 80. For that, we can use the condition gain multiplied by the bandwidth is always going to be constant. Let us compare the frequency responses of the open loop configuration and the closed loop configuration. In the open loop case, cutoff frequency is Fc. In the closed loop case, cutoff frequency is Fc dash. You can see that when the maximum gain is more, cutoff frequency is less. When the maximum gain is less, cutoff frequency is more. That is because the product has to be constant. Now, in the first case, bandwidth is from 0 to Fc. It is Fc minus 0 or Fc. In the second case, it is from 0 to Fc dash. So the bandwidth is Fc dash minus 0, which is Fc dash. So we can write open loop gain multiplied by the open loop cutoff frequency is equal to closed loop gain multiplied by the closed loop cutoff frequency. This is 10 to the power 5 This is 8. This is 80. So we can easily find out the new cutoff frequency. It is 10 kilohertz. Now, what we have to find out is the voltage gain of the amplifier when the input frequency is 15 kilohertz. It can be found using the expression AV is A max divided by root of 1 plus FC by F whole square. We have the closed loop configuration. So the maximum value of gain is the closed loop gain, which is 80. FC should be the cutoff frequency in closed loop configuration. It is 10 kilohertz. F is the frequency of the input, which is 15 kilohertz. So if we give the values, we get the gain. It is 44.4. Let us see the next problem. For the operational amplifier circuit shown, output saturation voltages are plus or minus 15 volt. We have to find the upper and lower threshold voltages for the circuit. Let us start by calling the potential at this point V. Here the input is given at the negative terminal and we have a positive feedback. What we have is an inverting Schmidt trigger. Let us start by marking the potential over here as V and applying KCL there. If I take the direction of current flowing through the 10 kilo ohm like this, then that current will be V minus V out divided by 10 kilo ohm. If I take the direction of current flowing through 5 kilo ohm like this, then that current will be V minus 3 volt divided by 5 kilo ohm. According to Kirchhoff's current law, the sum of these two currents should be equal to 0. Simplifying this equation, we can find a relation between V and V out. V is V out plus 6 divided by 3. We have to find the upper and lower threshold voltages of the circuit. When V has the upper threshold voltage, V output will be plus 15. So to get the upper threshold voltage, let us give the value plus 15 to V out. That gives us 7 volt. When V has the lower threshold voltage, V out will go to minus 15. So to get the lower threshold voltage, we have to give the value minus 15 to V out. That gives us minus 3 volt. Option B is correct. Let us see the next problem. For the circuit given in the figure, R1, R2 and R3 are equal. They are all equal to 1 ohm. L is 1 microhenry, C is 1 microfarad. The input V in is cos of 10 to the power 60. What we have to find out is the overall voltage gain of the circuit. Let us start by dividing the circuit into two. For the first part, input is given at the non-inverting terminal and we have a negative feedback. So we can consider this as a non-inverting amplifier. Let us take its output to be VO1. Now, the output of the first part is fed into the negative terminal of the second OpAmp through a resistor and a capacitor. Here also we have a negative feedback. So we can consider the second part to be an inverting amplifier. Let's take the first part. Here we only have R1. So the net impedance is just R1. Here we have L. So in S domain, the impedance can be written as SL. Since it is a non-inverting amplifier, we can write VO1 by Vin is 1 plus R1 divided by SL. Now R1 is 1 ohm and L is 1 microhenry. So giving the values, we get 1 plus 1 divided by S multiplied by 10 to the power minus 6. We can add these two and write it like this. S multiplied by 10 to the power minus 6 plus 1 divided by S multiplied by 10 to the power minus 6. Let's go to the second part of the circuit. Input is VO1, output is V out. This is an inverting amplifier. Z2 is just R3. Z1 is R2 plus 1 by SC. So we can write V out by VO1 is equal to negative of R3 divided by R2 plus 1 by SC. It is negative Z2 by Z1. Again R3 is 1 ohm, R2 is also 1 ohm, C is 1 microfarad. If we give the values, we get minus 1 divided by 1 plus 1 by s times 10 to the power minus 6. Let's multiply the numerator and the denominator with s multiplied by 10 to the power minus 6. That gives us this. Now, to get the overall gain, what we want is V out by V in. But for that, all we have to do is take the product of V out by VO1 and VO1 by V in. Because then VO1 and VO1 gets cancelled and what we have is actually V out by V in. Now, V out by VO1 is what we have over here. VO1 by V in is what we have over here. So technically, we just have to take the product of these two. You can see that what we have here in the denominator is exactly what we have here in the numerator. So these two will get cancelled. Also, we have the same thing in the numerator here and in the denominator here. So these also will get cancelled. The only thing that will be left is the negative here. So V out by V in is minus 1. The overall gain is minus 1. Let us see the next problem. The OpAmp in the circuit has an open loop voltage gain of 100. Its input offset voltage is 5 millivolt. It can be seen over here in the circuit. The amplifier is ideal and the input is 25 millivolt. What we have to find out is the output voltage in millivolts. Here the only problem we have is that the open loop gain is given, but our circuit has a feedback. So we have to find the closed loop gain. One more thing to be kept in mind is that there is an input offset voltage. We have a 5 millivolt in series with our input, which is 25 millivolt. So the net input is going to be 5 plus 25, that is 30 millivolt. Now let's find the closed loop gain. For that, first we'll find the feedback factor beta. Beta is R1 by R1 plus R2. R1 here is 1 kilo ohm, R2 is 15 kilo ohm. So R1 by R1 plus R2 will be 1 by 16. Now the closed loop gain will be open loop gain divided by 1 plus open loop gain multiplied by beta. This is 100, this is 1 by 16. So by substituting the values, we get 1600 divided by 116. We have everything we need. Output voltage will be gain multiplied by the input voltage. Gain is this, input voltage is this. So we get our output to be 413.79 millivolt. Let us see the next problem. In the OpAmp circuit given, zener diodes Z1 and Z2 clamp the output voltage VO to plus 5 volt or minus 5 volt. The switch S is initially closed and it is opened at time t equal to 0. What we have to find out is the time t1 at which VO changes its state. Let us figure this out. Before we do anything, I'll mark the potential over here as VB and the potential over here as VA. The output I get over here will be called VO1. As always, the most important rule to solve any circuit problem is not to be scared of how the circuit looks like. For example, see what I'm doing here. Let us model this circuit at t equal to 0 plus, which means when the switch is just opened. Before the switch is opened, you can see the capacitor is shorted, which means it will not have any charge stored in it. Now, at t equal to 0 plus, let us open the switch. Now, the capacitor has a path to get charged. But we know a capacitor cannot charge instantly. So when the switch is just on and it is about to charge, the capacitance can be modeled as a short circuit, like this. Now, the potential VB is plus 10 volt. Let us write it down. When the switch is just closed, that is at t equal to 0 plus, VB is plus 10 volt. Now, what will be VO1? To get the value of VO1, we have to understand this OpAmp. It is getting the input at the negative terminal. Plus, it is getting a positive feedback, which means it will essentially act as a Schmitt trigger. So the output is going to be saturated. Since it is inverting, for an input of plus 10 volt, we'll get an output of negative 10 volt. So we can write VO1 is minus 10 volt. Now we have two zener diodes over here which will clamp the output at either minus 5 volt or plus 5 volt. Since we are getting minus 10 here, the clamping will be done at negative 5 volt. Vo is minus 5 volt. Now what we have to find out is when the output will switch from minus 10 volt to plus 10 volt. We know the next switching will be when VB becomes greater than VA. To find out when that happens, first we need to know what is VA. VA is the potential that we get over here. If you look closer, you can see that we have a voltage divider here. Vo is being divided between 4 kilo ohm and a 1 kilo ohm. Out of that, whatever is dropped across the 1 kilo ohm becomes VA. So VA will be Vo divided by 4 plus 1 multiplied by 1, and Vo right now is minus 5. That gives us VA is minus 1 volt. So the next switching is going to be whenever VB becomes greater than minus 1 volt. Let it be there. Let us now see how the circuit will look like at t equals infinity, which means after a long time. After a long time, the capacitor will get completely charged, which means it will not allow any more current to pass through it, and we can model it as an open circuit. At that time, what will be VB? The circuit is open here and here. So this point does not have any connection to the plus 10 volt. But it is connected to the minus 10 volt through the 10 kilo ohm resistor. Now, what will be the potential drop across the 10 kilo ohm resistor? For that, we have to check if there is any current flowing through it. Obviously, current through 10 kilo ohm cannot flow through any of these paths because the circuit is open. It also cannot flow into the OpAmp because our OpAmp is ideal. So technically there is no current flowing through the 10 kilo ohm. That means there is no potential drop across it. Potential drop across the 10 kilo ohm is 0. So the entire minus 10 volt will be dropped over here. So VB is equal to minus 10 volt. So at t equals infinity, the capacitor 100 microfarad over here has a 10 volt on one end and minus 10 volt on the other end. So the net potential across the capacitance at t equal to infinity is 10 minus minus 10, which is 20 volt. Let us now try to find an expression for the voltage drop across the capacitor as a function of time. We saw that at t equal to 0, the capacitor was modeled as a short circuit, so the potential across it is 0. At t equal to infinity, it has a potential 20 volt across it. So we can write Vi is 0 volt and Vf is 20 volt. Now, for such a capacitor, potential drop across it as a function of time can be found using this expression. It will be Vf plus Vi minus Vf e to the power minus t by tau. Tau is the time constant. We know it is RC, but which is the RC circuit we are talking about? See, when the capacitor charges, it charges through the 10 kilo ohm over here. So to find RC, we have to multiply 10 kilo ohm with 100 microfarad, which basically is 1. Also, Vf is 20 volt, Vi is 0 volt. Let us give the values. We get 20 plus 0 minus 20 e to the power minus t by RC. Just like we said, RC is 1. So we get 20 minus 20 e to the power minus t. Let's take a look at the circuit again. We have a plus 10 volt over here, out of which some potential will be dropped across the capacitor. Whatever is left is what we get at point B. So we can say VB is actually 10 volt minus the potential across the capacitor. VB is 10 minus VC, but VC is this much. So we can write it this way. VB becomes minus 10 minus 20 e to the power minus t. We have already found that the OpAmp changes its state when VB becomes minus 1 volt. VB is this much. So we have to equate it to minus 1 volt. That gives us 20 e to the power minus t has to be 9, or e to the power minus d should be 9 by 20, or e to the power t should be 20 by 9, which means the time t at which this happens is log of 20 by 9, which is 0.798 seconds. So the switching will happen at 0.798 seconds. Let us see the next problem. There is a PIN photodiode of responsivity 0.8 ampere per watt. It is connected to the inverting input of an ideal OpAmp. VCC is 15 volt minus VCC is minus 15 volt. Load resistor RL is 10 kilo ohm. 10 microwatt of power is incident on the photodiode. What we have to find out is the value of photocurrent through the load. Now, the photocurrent generated by the photodiode will flow from the N side to the P side in this direction. Let us call it I0. Then, I0 divided by the incident power will be 0.8. It is given that the incident power is 10 microwatt. So, we get I0 is 8 microampere. Now, I0 is the same current that will be flowing through the 1 mega ohm. Because since the OpAmp is ideal, no current can flow into the terminal. So all of I0 will be flowing through the 1 mega ohm resistor, giving it a positive potential here and a negative potential here. Since the value of the current is 8 microampere, the potential drop across the 1 mega ohm will be 1 mega ohm multiplied by 8 microampere, which is 8 volt. Now, using the virtual ground concept, here we have 0 volt. So here also we have 0 volt. Now if you apply KVL in this loop from VO to the virtual ground, you can see that VO will be equal to minus 8 volt. Since VO is minus 8 volt, we can easily find the current that will flow through the 10 kilo ohm, which is our load resistor. Because the load resistor has minus 8 volt here and 0 volt here. So current will flow in this direction and the value of the current will be 0 minus minus 8 divided by 10 kilo ohm. IL will be 8 divided by 10k or 800 microampere and the direction is upwards. So that's all about it for today. See you in the next video and please don't forget to subscribe.